One last variation that we'll do in this section on variations and extensions is the notion of combinations of indistinguishable objects. The use of the word combination here implies that we don't care how they're arranged, and there'll be several of a given type and maybe more of a different type. So there are certain types that we might have. So as a lead-in example to explain the kinds of things we're doing here, we'll ask the question, how many different collections of 32 Skittles are possible? And just a reminder, Skittles come in 5 colors: green, yellow, red, orange, and purple. I believe those are the colors. And so 2 different collections would differ just based on one of the colors having a different number of Skittles. There being different number of Skittles of a certain color. So it's just how many of each color that distinguish a particular combination or collection of these. So what I've done is I've laid out 32 stars. So the stars represent the Skittles given by stars. And of course they're not given in any color here, but the question is how many of these would be green, not which ones in particular, but how many would be green, how many yellow, and so forth. So a nice way to do that, where we have a certain number of types and we only care about how many of each type there are, would be to lay out stars for the total number of them and then to separate them by drawing a bar. So for example, if this collection had 1, 2, 3, 4, 5, 6, 7, say 7 greens, then I'll do this right here, and this side over here would be all the greens. Okay? And then maybe the yellows, for the yellows there are perhaps 4 yellows. So these are the yellows. Ooh, I don't know if you can read that, but those are the yellows there. And then perhaps we lost a star there. I don't know how that happened. Here we go. So perhaps for the reds, there are 1, 2, 3, 4, 5, 6, 7, 8. I don't know, 4, 8 reds. I'll just draw a line right there. 8 reds, and let's not get fancy here. There's that. How many reds? And then maybe the number of oranges is 1, 2, 3, 4, 5, and then the number of purples would be 1, 2, 3, 4, 5, 6, 7, 8. These are the purple, and these are the orange. So this collection we have green, 1, 2, 3, 4, 5, 6, 7, yellow, 1, 2, 3, 4, red, 1, 2, 3, 4, 5, 6, 7, 8, orange, I think I said 5, and then purple, however many are left. And there better be 9 there, right? 3, 6, 1, 2, 3, 4, 5, 6, 7, 8. There's only 8 there, so am I okay? 13, 12. Yeah, that's 25, 32. That's 32. So look at the scheme there now. The scheme has 32 stars, and they're divided by these bars. There are 4 bars to divide it into 5 groups. We only need 4 dividers for 5 groups. 4 dividers for 5 groups. So anyway, we can arrange these, this string of 32 stars and 4 bars would determine a collection and tell us how many of each color there are if we decide ahead of time to count them green, yellow, red, orange, purple in the order I have them listed here from left to right. Okay? Now, this is a string of 36, 32 plus 4 items, and we're choosing positions for 4 of the items. So there are C 36 positions, of which 4 are for the bars. For C 3642 ways. Now I'll make this a little more careful in the general statement. This method is called stars and bars. Again, it deals with having collections whose elements are of certain types that are indistinguishable from each other, and it's a matter of how many of each type we have. So the theorem tells us the number of possible collections of n total objects, the above was 32, of R types, the above was 5, is CNR minus 1, comma, R minus 1, or if we prefer, CN plus R minus 1 n. I think I may have said that first one wrong. CN plus R minus 1, comma, R minus 1. Now how do we get that? Well, this is equivalent to saying we have n stars for the objects separated by R minus 1 bars to get R groups. So it would look like something like this. I'll just do a few of these. So type 1, indistinguishable, type 2, and type 3. In this case, 3 types of things. R is equal to 3 here. So, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. N is equal to 10 in this little example here. And so whatever these 3 types of objects are, there are 3 of type 1, there are 2 of type 2, and in this scheme there are 5 of type 3, but the number of ways we could get that would be C 10 plus 3 minus 2, minus 1. 3 minus 1 is the number of bars. 3 minus 1 bars to divide it into 3 groups. And then 3 minus 1 here, or C 12 2, like so, which is 66. Okay, so that's the stars and bars method. I'll do another example of this in the next very short video.